let's open a notebook and let's start to explore how to code the discrete convolution algorithm to compute filtered images. First, we need to load an image and some support functionalities. So by clicking on the folder icon on the left, a sidebar appears showing the list of available files. Let us click on the Upload button and select from your local file system the file helperfunctions.py and the image part.png. Then we need to import the NumPy and Matplotlib modules. Then from the Python imaging library, we import the module image. And then with this syntax, we import all the functions contained in helperfunctions.py. That will help us visualize the results. Let us load the image as a matrix. So first we use the image module to load the image contained in part.png. Then we convert a color into grayscale using the method convert and the option L. And finally, we convert this grayscale image into a NumPy array using this syntax. With the instructions type and shape, we can extract some information on A. As we can see, it is an n-dimensional NumPy array of shape 12 by 12, matching the number of pixels of the image. So how does a two-dimensional NumPy array work? To access an element, we use square brackets. So for instance, the element in position 1, 2 can be accessed as a square bracket 1, comma 2. We can also print the matrix A and note the values 0 corresponding to the black part of the image. Instead, by using imshow from Matplotlib, we can display the matrix as an image. We just need to specify that we are working with a grayscale image. Now we can implement local convolution applied to a specific pixel in position ij, as in the pseudocode. Let us create a function called local convolution. This function takes as input the matrix A, the kernel K, and the indices of the pixel I and j, and returns the value of the filter pixel. First of all, we declare the variable v and set it to 0. Then we introduce two for loops, one to access the rows and the second to access the columns of the kernel. And notice that these two loops are nested, meaning they are one inside the other. Now for each position in the kernel, we compute the product of its value and the corresponding pixel in the image, and we add it to v. Finally, we return v, which is the value of a single filter pixel. Now, to process the whole image, we need to loop over all the internal pixels, considering all the rows and columns except the first and the last. For this, we create a second function called imFiltering that takes as input the image as a matrix A, the kernel K, and returns the filter image R. As we have seen, we only process the internal pixels of the image, so our filter image will be smaller than the original one. In particular, if rows and cols denote the size of A, the resulting matrix will be rows minus 2 by cols minus 2, and we can initialize it as a matrix of zeros with this syntax. Now we perform two loops, one for the rows and one for the columns. And notice that the index I starts from 1 and ends before rows minus 1 to skip the first and the last rows, and similarly for the columns. Now for each ij, we perform local convolution using the function we wrote before. And we store the result in R, which, remember, is smaller than A. And pay attention here. In particular, we store the result in position I-1, j-1, so that indices start from 0. Finally, we return the result. And we are almost ready to use this function, but first we need to declare a blurring kernel. We can create a 3 by 3 matrix of 1 and divide it by 9. And now we call the function imFiltering to compute the filter image. Finally, we use the function compare images to visualize the original and the blurred image. As you can see, the image has been blurred, but it also became a bit smaller. So how can we avoid this side effect? We can perform padding on the original image before filtering. So we basically add pixels all around it so that each pixel has 8 neighbors. And the easiest option is to simply add black pixels. We can do it in this way. We create a larger matrix AP, which has 2 rows and 2 columns more than A. And then we can copy A into AP, going from the second to last rows, and similarly for the columns. And now we can repeat image filtering, giving AP as an input, and we obtain a blurred image which has the same size as the original. So finally, we can replace our photo with a version that respects privacy.